Okay, good morning, everyone. Welcome to this IAS Distinguished Lecture. Today we are very happy to have Professor Jian-Qing here. Professor Jian-Qing is Frederick Moore 18 Professor of Finance, Professor of Statistics, Professor of Operation Research and Financial Engineering at the Princeton University. Professor Fan has been awarded the COPS President's Award, Morningside Gold Medal for Applied Mathematics, Guggenheim Fellow, Xu Baolu Prize, and Guide Medal in Silver, among many other awards. And he is also an academician of Academia Sinica. Professor Fan is a great leader of several academic societies, including statistics, financial econometrics, and also data science. Professor Fan had been the president of the Institute of Mathematical Statistics, IMS, and also the president of the International Statistical Association, International Chinese Statistical Association, ICSA. And Professor Fan is also the editor, or has been the editor for several leading journals, including Annals of Statistics, Journal of Econometrics, Probability Theory and Related Fields, Journal of Business and Economic Statistics. So today we're very happy to have Professor Fan here to talk to us statistical machine learning for financial prediction and inference. Welcome.
Okay. And among so many wonderful introductions that she has made, she forgot I'm also a member here. I'm very proud to be a member here, and I'm being, talking with you. So let me outright, right? So when I talk about this, it's not like I would like to talk on this. I mean, it's nice, right, to be this, and there's a very good reason, right? So we are we are living in a very great time, right? Data revolution. Digital society, and of course, among all those, really, when we are talking about real content, is the technology that meet with the society needs, right? And among those, I think statistical machine learning standing out, right? So when we are talking about AI or whatsoever, the real content is still it's still machine learning, and then of course, finance is always an important subject that concern the all household. So today I just contribute a little bit to these topics, and hopefully that let me give an introduction to connecting what we are doing in financial econometrics to the machine learning and inference. So I have been working on this area for at least 15 years, right? So, and one of our late books that back at least 10 years now finally about to come out in this area. So here's the outline of my talk. I'll give you an introduction, and then I'll give you a principle of robustification. So my emphasis today probably is more on methodological power rather than on statistical or econometric properties, right? And then I'll talk about factor models, which I will connect you with unsupervised learning, right? So I'll talk about forecasting bond risk premiums and testing of pharma French models, and then finally I use these as a factor adjustments and can give you conclusions. So let me begin with the introduction, right? So since I'm talking about statistical machine learning, the first question you may ask is, what is machine learning, right? This is very natural. And then, of course, if you ask Tom Surgeon, you say AI is a gorgeous name for statistics, which, I agree to some extent. If I ask my friend Michael Jordan, he and I talked the same in World AI Conference, he is more brave. He said AI is statistics, right? So now, what is it? Don't get emotional, right? What is it? So here is my definition. And I put this in my teaching, in my book, right? Is a scalable statistical algorithms that combines expertise from statistics on how to extract information from the data. In other words, the first part is statistical modeling or econometric modeling, the same meaning, and with computational idea that enable efficient implementation on large scale of data sets. So in other words, the real content behind us is the statistical modeling combined with computational ideas. Optimization together with statistics is a little bit more than statistics. I want to say that, right? And then example of this, whatever you mean example, is Tom Surgeon's example of gorgeous name for statistics, or deep learning, or machine learning example. It's still deep learning, right? It's a very nice name, right? So in which people want to classify, let's say, images, right? Like this. Classify images, and they build up a model in 90s, right? So, that's called, neural network, and now called deep learning, the same thing. The idea is that you apply, you create index using financial term that is linear combination of your raw inputs. And so this creating many indices, and then you apply nonlinear gating, nonlinear operation, and you use this as an input. You apply again, creating index, and you do linear gating, and at the end of the day, you train the sample, and you learn all those. Right? So if there's another opportunity, I will tell you why deep learning work and what is mathematical insight, what is the algorithm. But this is not today's meaning. Like today, I give you this is just to say what is machine learning to begin our theme. Now, what are the commonly used techniques in machine learning? Right. So if you ask everybody, people will say regression and classification tree. And this one, in terms of abstraction, there exists a y variable. There's a response variable that we call supervised learning. And there's also like a social network. Most of my talk will be combined both. So there exists like a clustering, like a social network, or clustering. So in this case, there's no y variables, right? So we give a name called clustering. And among unsupervised learning, there's a very strong components in finance that always been permanent feature. That is, principal component analysis is being regarded as unsupervised learning. So now, of course, after saying this, I say, okay, today you're standing in so many of audience, speaking with confidence. What does the next question you logically ask? What makes financials so special, right? So in other words, what is financial data differ from biological data? Then we have to specialize into finance. And here is a few important stylized feature in finance, right? So that time varying volatility or time varying dynamics, right? And this part is always been taken care when we analyze data. We localize the time window to reflect time locality of financial dynamics. So this part usually done by this. And then, of course, the next people will say, well, we are talking about tail products, we are talking about tail risk, and so everybody knows there's heavy tail. And today I'm going to give you a very simple way to deal with, a heavy tail, which is a truncation principle. And then third, people will say, well, when you do portfolio choice, when you do macroeconomics, right? So you measure some kind of fundamental of the economy in the society. So therefore, there are cross-sectional dependence. And today I'm going to give you a bit on augmented factor models. And the augmented factor model is inherently related to principal components, and therefore is inherently part of unsupervised learning. Okay, so this is how I connect all what I talk with machine learning. And let's begin with cross-sectional dependence, right? Factor models. And this is really every country saying about factor models, right? Rising tide raises all the boats. This is exactly what factor model means, right? So there's unknown latent factor or invisible hands push all stock up and down, right? So this is FT is the latent factors, and YT is the panel of data you observe, like stock return or macroeconomic time series. And then plus, just like rising tide, every boat still floating around their own locality. So this is UT is idiosyncratic components. So writing in components, right? So basically saying ith stock or ith macroeconomic time series, depending on latent factor in certain loading, factor loading, plus idiosyncratic noise. And typically we need, and as I will show you in examples, that we need, to know what is the factor loading, gamma, and what is latent factors for risk return, trade-off, for regression and prediction, even for discovery controls when you are talking about doing multiple decisions and so on. And what are the typical tools for uncover those latent factor and those idiosyncratic components are principal component analysis. I know my friend Yuan Liao is here, and Liao is here, so he will say this is low rank matrix, right? So we are going to recover low rank matrix. Everything the same, right? So, so the typical tool is principal component analysis, which is equivalent to high dimensional spike models. And which is equivalent to a factor model for high-dimensional spike models. And as we know, if I really want to mention, what is principal components, right? So is really fundamental tools to social machine learning. So if you say regression to statistics, I think PCA to machine learning, I think they are analogy, very similar. So I could say many examples of application of PCA, but this is not my today's topics, right? But in order to uncover this latent factor and this idiosyncratic noise, our traditional way always require both number of assets or number of macroeconomic variable or panel had to be large and time series had to be long. And this is not always possible to just increase increase the time series because of time varying feature of financial markets or of the real world. So you cannot just simply increase, say, hey, 30 years. In 30 years, something must have to change, right? So you cannot just simply increase T. Now the question is, how do we increase information content? Very naturally, right? And typically, when we analyze these kind of data, or when we analyze real data, so is more than just, the plane you observe a panel. You have other information. So let me give you two examples, right? So the first example is typical in financial markets, let's say in the celebrated, let's say pharma French 3-factor or 5-factor models, right? So you observe, let's say, market factors, size factors, value factors, investment, and so on. So you observe 5 factors. So you're asking, hey, is these factor model adequate? In other words, is 5-factor adequate explain the cross-sectional dependence among financial assets? So in this case, it's very clear we have information I call X, XT, which is pharma French factors. And the latent factor that drive the dependence among those stock returns depends somehow on pharma French factor, but may not be 100%, right? So in other words, it depends somehow on pharma French factor, and then plus idiosyncratic components. And now the question I ask is the idiosyncratic component equal to 0? So that pharma French factor is 2. Right? So this is be one example of this, and this is very different from the traditional efficient market hypothesis type of testing, which testing basically whether the alpha, the assets pricing alpha equal to 0 is correct or not. So let's not get too detail on that. And then the second example, also very typical, is forecasting bond risk premia. So in this case, I have a time series. ZT denotes, let's say, U.S. government bond risk premia with maturity could be 2 years, 3 years, 4 years, and 5 years. So let me just save time not to explain what it is. This is a variable, let me call Y variable I want to, or the dependent variable I want to forecast. And this is very typical, right? So you have, let's say, 131 disaggregated macroeconomic time series. And if you are interested in that, it's very nice correct on Michael McCracken's website about those 131 macroeconomic time series. And in addition, you have also 8 aggregated macroeconomic time series. In this case, let's say X1 would be linear combination of 5 forward rates, X2 would be GDP, and so on, right? So let's say X5 is real industrial production. This is the aggregated of industrial production among many of those, let's say, disaggregate in each sectors, right? So this is aggregated macroeconomic time series. And our interest is, so in other words, we have two pieces of information. They are all related to US government bonds, but they are not identical, right? And just thinking them as together as 139 is a mix of two things at very different scales, right? And similarly, so if I have microarray data, which are genetic data, and I have clinical information, right? I mean, if you just simply mix them together, it's not a very, how to mix them together as an X variable. It's not, they are all X variables, but they are very different kind of X variables, right? So in our case, this is my notation. I know maybe confused you a little bit. I use X, Y, Z. I could use W, X, Y, right? But unfortunately, I use X, Y, Z here. But both X and Y is to predicting Z, right? So this is the same. You could imagine that if you are a bioinformatician, this is your clinical information, this is your genetic or genomic information, and this is your clinical outcome, right? So you cannot simply combine them because they are different. So okay, so these are two examples. I said that you have also other variables. Now my question is, how do we use covariate information? Principal components just typically use this kind of information, right? Or just use this kind of information. How do we use those information? And then the next question we mentioned at the very beginning is, how do I deal with heavy tail data? And let me begin with deal with heavy tail data because it's relatively simple. I can actually talk in a few minutes, right? And this is, first, I want to show you an evidence what I say is true, that heavy tail distributions is everywhere in modern statistics and machine learning. I mean, as we just mentioned a few moments ago, financial returns, macroeconomic time series, typical heavy tail, and high throughput data like microarray proteomics and fMRI data typically are also machine scanning data, also heavy tail. And just by chance alone, when you have tens of thousands of variables, right? You cannot expect everybody to be a Gaussian data, right? So this is quite odd with theoretical machine learning on sub-Gaussian or sub-exponential assumption. And so how do we deal with this? All right, so here's one example just to prove what I just said. In this case, I have 131 macroeconomic time series we just mentioned a moment ago. I decided to plot their kurtosis, right? So that I will compute 131 kurtosis, and I display the distribution of kurtosis here. So among those 43, right, a quarter of them, a third of them has heavier distribution than t-distribution with degree of freedom 5. So if I want to do the same thing for financial, let's say, assets, I will get in the similar conclusion, right? So a heavy tail is there. And so now the issue is, how do we deal with heavy tail data? So let me begin with the most basic and fundamental is, you will laugh, as simple as I observe NIID data with mean mu and variance sigma squares. And my interest is very humble, just estimating this mu. And so this is very first, step 101 learning, right? So this is very humble. The difference is I take normal away. So there's no normal distribution here, right? As simple as that. And then, of course, I do a very simple truncation principle. Say, hey, if my data bigger than tau, or let's say 3 standard deviation, I truncate at 3 standard deviation, right? Less than 3 standard deviation, I keep it. So in other words, when it is less than negative 3 standard deviation, I keep a negative 3 standard deviation. Big, I keep that way, and then doing this in between, right? So now let's see what is kind of result I have. When I do this truncation, I create bias. And when my tau truncation is at high level, let's say square root n of my standard deviation sigma here, then magic happens, right? So sample average of my truncated data deviate from population average, population mean, t standard deviation away, right? So I look at the t, so in other words, I look at the tail of the sample averages, the distribution of the sample averages will go to 0 exponentially fast, right? So this is typical people call exponential concentration. So in other words, you give me a data with only second moments, and you do truncation, the behavior of my sample average is pretty much as you do Gaussian data. When you calculate the sample error Gaussian data, you have the same property. So in contrast, if I do nothing, that is, I take tau equal to infinity, I just calculate usual sample mean, right? Then just by Markov inequality, you could easily see that the tail you can ever hope for is 1 over t squared. So in other words, a very short summary is truncated mean will have Gaussian tail, the usual mean will have Cauchy tail, right? So this is a very different. Now, you say, well, if this is the case, why when I learn in Stat 101, professor doesn't emphasis on this? Because professor only do that sample mean once. When I compute sample mean once or 5 times, I'm not really afraid of Gaussian tail or Cauchy tail. But when I do high-dimensional statistics, this is very fundamental to high-dimensional statistics, right? So let me give one context in the case where finance people are concerned about, right? Calculate, let's say I have Russell 3000, right? So I want to do portfolio allocation. So I need to calculate the sample covariance matrix of 3000 covariance matrix, right? So let me just give you a little bit nicer one, say mean equal to 0, so save our conversation. Then you have to calculate the covariance matrix, which is really just the mean of the cross product of random variables. So how many of them? There will be 4.5 million, right? So you calculate 4.5 million, you estimate 4.5 million sample means, right? So this is very different from classical statistics. You estimate 2 sample mean or 1 or 5, right? So this is a lot, right? So in other words, so if you really want to get a robust covariance matrix as if you have Gaussian data, then you have to truncate the data, right? So you could truncate the data because you are just estimating each of these sample means. Then because of your Gaussian properties, tails, right? So even though I have 4.5 million elements, you are asking what is the maximum components-wise estimation error? Well, this component-wise estimation error would be increased with dimension error in a logarithmic order. So in other words, because of Gaussian tail, it will not increase too much. And if you look at whatever the covariance inputs for matrix completion, for whatsoever, this is all really needed for covariance regularization. This is really all you needed, plus other matrix structure to make you have the result you want. So in other words, by doing a truncation, you bring yourself into a very nice world, a Gaussian world, right? So that we can imagine of. So of course, sometimes if I do regression and I truncate in X variable, I truncate on Y variable, is a lot of inconvenient. Not only that, truncation in X variable for regression, while mathematical, you could prove the same properties. It's not the same thing that people usually advise, right? So it's typically what we do this just to please mathematics, not necessarily what we do. So in this case, you may decide to truncate on the loss. And in other words, when you are less than tau, you keep using quadratic loss, and when you big than tau, you big than that. So in other words, if I look at this curve, so let's say this is tau, is a quadratic here, and then linear outside, right? So this, then of course sample mean is just the minimizer of this. Now we are doing truncated one, so it would be mean. Now people may ask me, well, why you call adaptive Hilbert and why you draw so many graphs here? I basically was trying to say emphasis is tau is depending on n, right? So tau is how to adapt it to the data, to the scale of your standard deviation, and to the sample size. So when this happens, you can show the same concentration equality, and this would be way more convenient when you analyze for regression. So I have given you a very simple principle of truncation, basically saying inverse, right? Back to here, inverse is like this, right? So if you do truncated mean, your mean behavior will be as if you are drawing from Gaussian data, and if you don't do it, it will be just like Cauchy data, and this would be very useful for high-dimensional statistics. Similarly, if you are doing regression type of analysis, sometimes it's more convenient to truncate on the loss. You have similar property as we promised here. Now, let me just give you a very quick utility, right, empirical applications to show you that a simple principle actually help you in analyze data. And this one is that we have fun of doing like high frequency trading. So in which that, well, I mean, like one of my students who invited us for dinner last night, right? So he was, and indeed a fancy dinner, by the way. So everybody agreed it was a very fancy dinner, right? So he, actually the project coming from him, by the way. So he has, let's say, 365 signals, right? And he created or handmade or whatever. Nowadays we can use machine learning to learn those too, right? And or at least machine assisted to learn those too, and to predict a target, profitable target. And the profitable target is just a smooth price from current time to, let's say, 10 or 15 milliseconds later, right? And then the signal is the feature that you obtain just before time t from historical data. And of course, for our exercise, we just use out of sample R squares, and without talking about complication or everything, right? So we just do a very simple, principle. So for this particular one, that they give us one stock, right? So it will be like a 4-month data, and well, people say, well, not 3 months. I think 21 days is about 4 months, right? Per trading day, 4 months, and then. Is about 0.5 million and 1.8 gigabyte. You could imagine that if you have 10 years, I have to multiply by quite a large of this number. And if I have 2,000 stocks, we're getting very messy in terms of computation, right? And then the first thing first, right? So this is the target or Y variable I was given. And these are the 365 features. So I correlate each features with those X variable with Y. So I got 365 correlations. So if you look at correlation, the correlation range is only from 0.1 to 0.15. So each signal is pretty weak in terms of correlation, right? And this is the same plot, just a histogram of those 365 correlation of each signal correlate with this Y. And again, this will be range just from negative 0.1 to 0.15, very weak. And then, of course, naturally, we do say, hey, let's combine together, right? So we got a multiple correlation. And in this case is a simple linear regression. And this, let's set it as a benchmark. So if I do this out of sample R square, is about 0.1. So is much bigger. Or if you take a square root, correlation is about 0.3, right? Or 0.35. Right, so now if we do truncation of the data, truncate at tau, I don't know what tau to choose, so we decide to just do a family of taus here. Right, when tau go to infinity, these two curves eventually match because there are no truncation anymore. Right, so they will be eventually match, and then the optimal choice, right, so is about here, so about 1.78 in this region, and this gives improved multiple R squared by 0.04. I mean, they're pretty happy. And then, of course, we are not doing this simple linear regression model. We also do other models, and we found that the truncation does help, right? So this is a very simple example to show you that, a very simple robustification principle will help you better prediction power. Right? And then the second one is, again, just like forecasting U.S. government bond risk premia. So I will given ZT, and I will also given this YT and this XTs. So I'm going to use these to predict that, right? So again, I could do robust principleification. I could do just naive, right? Let me do the most naive one. So I extract the features from those 131 macroeconomic time series, and this one in economic we call diffusion index, right? So let's say, among 131 macroeconomic time series, I extract the 5 principal components plus those 8 aggregate one, right? Now they are in the same scale, so I have 13 variables. So if I use those 13 variables to predict U.S. government bond risk premia, it will be right. I mean, I will get. It will be called principal component regression. So in other words, this X star you use to predict bond risk premia is the 8 aggregate macroeconomic time series plus 5 principal components, extract from disaggregated ones, right? So this provides a benchmark of out of sample R squared about 24%. Now, if I apply everything, the same technique, just apply robust principal components, robust principle in regression as well as, factor extraction, multiple R squared jump quite a lot. Right, the same way for 3 years, bond risk premium jump to here, for 4 years jump to here, 5 years jump to here. So this just give you a very quick example, just how you could actually improve prediction by just doing a simple truncation principle. And this is very cheap. Whatever software you use, you continue to use, right? So you just truncate the data and run the same. Now let's do a little bit more, right? So let's blend a little bit more of our augmented variable into factor analysis. And this is our model, right? So, okay, so here I have factor models, and I do not know what is the latent factors, but I'm not blind either, because I have covariance information, right? In one application, I have aggregated the macroeconomic time series as my X variable. In the other occasion, I have, Pharma French factors as my proxies, right? So in other words, market factor unknown to me, but I say can be partially explained by your observed macroeconomic time series, plus some kind of, some kind of idiosyncratic components. Now, so how do we do, right? And I say the method is surprisingly simple. You will laugh on it, and let me say the method first, right? So okay, so let's say using those 131 macroeconomic time series. So for each macroeconomic time series, you regress on each of these macroeconomic time series, this aggregated one, you regress on aggregated one, you got a fitted value, right? So this would be, and now I just do principal components analysis based on fitted, Y rather than original Y. So the same way, if I have 3,000 stocks, for each stocks, you regress on Pharma French factors, and then you get a smooth or a fitted value and do principal component based on fitted values. So, and this one we give a name called projected principal components because you are projecting data into the space spanned by your covariance, right? So then now you just run principal components analysis on this. And now you ask me, what is the benefit? I say, well, the benefit is you will improve the accuracy even though when your number of assets is small. Well, people say this may not be a big deal. Now, I'll ask why in the next slides. I'll answer you in the next slides. But I know nowadays, just lately, I'm very excited to see that when we publish the paper in the Annals of Statistics, it has been applied by a number of people using, use that in the, actually when we do it, it's not in this setting, it's in we assuming that the factor loadings change over time through state variables. So I have seen nowadays that a lot of application of these techniques in assets pricing. In that you're thinking loading is dependent on, let's say, firm-specific covariates. And this method could be continued to apply. It's just like, in this case, I have row and columns, right? So I probably do smoothing on columns. You could do smoothing on rows, right? So it would be very similar. And the projection here, we're using a very simple methods, but you could really use deep learning if you like, because all I really need is to do something, which I basically say smooth out the noise. So now let me try to explain you why such a simple idea work. And as I said a moment ago, this idea also applicable to assets pricing, in which people do believe, right, the factor loading change over time, and it change over time through state variable of your companies. And this I see a lot of application nowadays, at least 5 to 10 papers in finance. Very exciting area that people are working on. Okay, so here's the basic idea, right? Let's recall the model. I use this this model to explain, because this model a bit easier to explain than when I talk about projection on firm-specific covariates. Okay, so this is the factor model, right? So I say this is the factor model. Again, this is maybe I'm still thinking of doing smoothing on each rows, each columns. But when you do firm specific, smoothing on each rows. Anyway, and the factor loading has this kind of expression, right? So it depending on, right? This FT is not completely unknown to us, but you have site information so that you can do this kind of decomposition. The part can be explained by XT, the part cannot be explained by XT. And what is the purpose of my projection, right? The purpose of my projection is smoothing, right? So I smooth YT on XT, which according to our model be lambda times smoothing FT on this XT, and whatever this information I have, or this is really just equal to that. Whatever this is, what I have, is compare this model with the previous model, right? So the smoothing is just purely remove this noise part. Right, so the smoothing is remove this noise part. So this is really what I'm doing. So when I'm doing projection of YT on XT, I really hope that my XT relate to this FT. So this guy is not 0, right? I call GX, and then this part be removed. So in other words, by doing this, right? So you remove the noise, so now it's become a row rank matrix, right? So this is exact row rank matrix. So, so in other words, the gamma you want are just the principal component of covariance of your fitted data. And this case is exact identification rather than, let's say, asymptotic identification. So this is a nice part. So now let me just summarize you the procedure that we have introduced so far. So first, you compute a high-dimensional covariance matrix using fitted data, and this part can use deep learning, can use kernel machine, can use complicated ones, and I see people use different kind of technology when you apply to firm-specific covariates. Okay, so this part you can do anything you like. One of your favorable machine learning or supervised learning algorithms, right? And then the second part is unsupervised learning, right? You do principal components analysis. You get the leading eigenvector of your covariance matrix of fitted data. And then the third one, of course, you are just projecting your data on these principal component analysis, right? So then in this case, I extract the latent factor using the covariance information. In other words, XT has already been blended into this process through fitting. And as I said a moment ago, this fitting is to remove this noise, right? This fitting is to filter out that noise. And now, of course, if you really care about what is this, the part can be explained by my XT, what is the part cannot be explained by XT, you just regress your fitted value on, or project your fitted value on your principal components, right? And this is just the difference between the two. So you can get all components out from this regression. So from this, this regression, and then how do we really do robust fitting, right? So the robust fitting, now I had to run regression. And in this case, I just doing a very simple sieve methods in which I do just basis expansion using these basis expansion to predict let's say large panel of data for each individual stock or for each individual macroeconomic time series. I fit on those XTs, right? And I do alpha t here to add into the robustification to it, right? So let me remind you what this rho alpha t is, right? It's a quadratic. When it's less than alpha t and then extend linearly outside, right? So this is Hilbert loss. We call adaptive Hilbert loss because the loss depends on sample size, depends on the scale of your data, right? And that now you just do sieve fitting and you get your fitted value. You can use any other statistical machine learning methods such as kernel machine or deep learning, whatever variable you like. And again, even I fit in the wrong model doesn't hurt you because as long as I could reduce this noise, I increase my signal, right? So in other words, even if you use the wrong model, as long as this part is not 0, I mean, you still doing the same thing. Yeah. So this is a nice part. So I don't really have to be correct. Now, what is unintended consequence of the first step? That is doing robust fitting, right? Or, I mean, I just again I just again plot those 131 macroeconomic time series, but this time is a smooth one, right? Smooth on XT, and I plot this, and this is now the same. Distribution of kurtosis, and as you can see that by doing projection, you get in robustness too, right? So not only, I mean, projection not only leads you to suppress the noise in here, but also help you, reduce the tail, right? So just looking at those, if I compare the kurtosis of 131 variables, right, with the kurtosis I showed you before, original time series. So let me go back, just we could relax a little bit, right? So from here, the tail was much heavier among 131 macroeconomic time series. Once I do smoothing, the kurtosis is getting much smaller, right? Okay, so this is, right? Now you compute the sample coherence based on fitted values. And here's a few just quick remark, right? So first, what is the choice for robustification parameter alpha t here, right? So this alpha t, when I choose very large, let's say infinity, is a least squares, right? So in this case, there will be an unbiased estimator. And when, in this case, it will depend very much on the tail. Right. So on the other hand, if alpha t is very small, very narrow, I create bias, but then I gain robustness. So there's a trade-off between bias and very robustness. And we basically say the optimal choice is like this. So this is a econometrics or statistical study getting that conclusion. And we do extensive simulation, which shows that incorporating XT does improve your estimation. And in terms of game, when the data is heavy tail, you will gain a lot. When data is light tail, you really pay virtually no price, right? And then, of course, as I said, we develop econometric theory to support that. So let me apply to forecasting bond risk premium. So again, I asked the same question, right? How well can U.S. bond risk premium be explained by macroeconomic time series? So I have two methods. One is conventional methods, right? So among 131 macroeconomic time series, I extract 5 latent factors, say, right? And then these 5 latent factors plus 8 variable macroeconomic time series give me 13 variables as my input or as my x variables, right? The other is our new approach, which is conditional, basically saying, hey, you smooth yt given this xt, right? So the factor is really the same estimation of the factor. I use capital F to denote a new methods used to extracting factor. And now you could just regress the bond risk premium on these newly extracted factors or principal components regression. And now in terms of prediction, I have 2 possible approaches, right? One simple linear regression, as we said before. The other is we could create a prediction index, right? Or prediction index by using, well, multi-index model, or is interrelated to what now they call deep learning model, right? Okay, so, and as I say, this xt could be just naive extraction of of the factor plus 8 macroeconomic times. This would be 13 variables, or just our conditional ones, right? Project PCA extract the factors, or you could combine these 2 together. And H function, it could be additive, that would be shallow learning models, or it could be other functions. Okay, so, and then, of course, this prediction in econometrics, sometimes we call sufficient prediction. So is really interrelated to deep learning. I mean, have really like 4 layers, right? So our basic assumption is there are latent factors, right? Latent factors that drive the outcome, right? But those latent factors also drive those input variables, right? So now when we do analysis, we are doing backwards, right? So from these input variables, I infer about those latent factors, right? And from those latent factors, I creating prediction indices to predict my outcome. Right? So this would be like a 4-layer neural network, right? And of course, our algorithm compared with neural network a bit more scalable because it's all doing principal component analysis and more explicit computation rather than using stochastic gradients methods and so on, and it's not over-parameterized model. And, well, of course, you can do a theory if you like. So let me not get into these details, but just directly show you the result of forecasting results, right? Again, our measure is outer sample R squares in terms of percentage, right? So if you see this big than 1, because I just multiply by 100. Okay, so this is the row that I showed you before. This is the simple linear regression. This is non-robust version of simple linear regression. I extract factor by using principal components, and then plus 5 plus 8 give me 13, and this is robust implementation. Now this is our new methods, right, of extracting latent factors by using projected PCAs. So you go from here to here just by using different methods of extracting latent factors, right? You increase multiple R squared by quite a substantial, right? And this is for 3 years, 4 years, and 5 years. You could increase at different scale. And then from here to here, or from here to here, you are really using slightly different, right? So you're using robust implementation of the same idea, right? And the robust implementation give you further gains, right? And now if I do further, let's say nonlinear prediction, right? So in other words, I'm creating like a multi-index prediction. You could gain further, right? So now this table you have to compare with previous table, right? So it's each cell here is from linear model to nonlinear model. It's gained further, right? For example, here, let's say taking any number, 32.6. Of course, it will not increase as much behind 4.5, right? And the previous number, let's say here, is a simple linear regression, right? If you do multi-index model, you increase to 31, and so on, right? So the biggest one for 2-year bond risk premium, we could get to 45% in terms of outer sample R squares from previous one, 38.1, right? So this just show you again, first factor gain is using different extraction of factors, right? Second game is that using non-robust to robust, and the third game is using linear model to nonlinear model, right? So this is each of those contribute to the final prediction games. But in contrast, if you use the most naive of all, right? So you just use those 8 macroeconomic time series to forecast bond risk premium, you'll have outer sample R squared, but it's not very, very big, right? Okay, so this is one topic I have seen. Then the other topic, of course, always curious me is, testing Farmer-French factor models. It's no doubt everybody will agree. Farmer-French factor model cannot explain everything, right? There are 2 proofs of it. One is there's still so many companies, trillions of assets being under management using factor tradings, right? Like a Farmer-French advised funds, right? What that name, but anyway, so let me create a test statistics, right? So at each time t, you can create war type of test statistics, right? At this standardized quadratic, right? So because you estimate the part cannot be explained by the factor, Farmer-French factor, right? And you just normalize this. So, whatever this W is, just estimate covariance, right? So you could easily imagine that would be like I have K factors here, so it'd be chi-squared with this degree of freedom K. Now I have T of those, so it'd be KT, right? Whatever it is, at the end of the day, this S statistics will behave like this, or more formally, when you standardize this, basically you have a null distribution of your test statistics you can use, right? So this is a very bypass, a very short way of bypass whatever has been proven. Now we apply to Farmer-French three-factor model and see how big that test it is, right? So this is, I apply first to the daily data, and we just lazy using 393 stock that survived during this period of the time. Of course, there's some survival bias, but anyway, so we just testing Farmer-French factors. So this is the test statistic that I draw you here. So this is three-factor models, is red one, the test statistic S I have. And what is the contrast? So it's around like 40, 50, right? What is the contrast? 1.96 is you're comparing with. So certainly p-value is extremely small. You easily reject it. This is based on like 3-month data, right? And this is Farmer-French 5-factor, a little bit better. Test statistics, a little bit better. And then, sorry, this is 3-factor, this is 5-factor. And then the red one is 5 factors plus 9 industrial sector factors. So it's all improved a little bit, but not really very much. Now you may argue, say, hey, Farmer-French, when they talk about it, they are talking about monthly data. You apply to daily data, and daily data have this and that kind of troubles and so on. So we do similar exercise for monthly data based on 60-month moving window. So at any time T here, I just use past 60 months to compute test statistics. Again, this is the test statistic that I have, and compared with critical value 1.96, only in the period where Farmer-French model was invented is more or less reasonable, and other period may not necessarily reasonable, right? So this is typical. I mean, I know you're laughing because most people doing this kind of exercise, right? So we reject most of the time. Of course, most interesting question is not whether Farmer-French factor model is explain the full market, is how much left there for those, quantitative asset managements, right, to create new factors, to realize some alpha. So we decide to compute this, right? So this is the part cannot be explained by Farmer-French factors, and this is the total that we learn from the market, what is the latent factor. So I just see what is the proportion of factor not explained by Farmer-French. So now I plot this. So it's a dashed line that we are probably looking at, the dashed line, and the scale is here. Scale is on this side. So if you look at it for, let's say after 93, the average maybe around 20 to 25, probably not explained by Farmer-French 3 factors. But it's probably less, maybe 15 by maybe Farmer-French 5 factors, right? So, so in other words, this statistic tells you there are still a certain percentage of unexplained factors that you really is there that you can do factor trading. So the last part of my machine learning statistic one is a very simple software, just in case that you would like to use. And it's a very simple idea. Maybe, again, just like as simple as, so all of my ideas are very simple. Like the first one is just doing truncation. The second one is just doing projection. The third one I basically just in doing factor adjustment. So if you happen to use R, there are 2 software packages there, right? You could just install packages or issue a command like this, and you'll be in business, right? So let me begin with what I'm doing. So this again, I'm applying. This time is not using factor to do regression, but using or to do prediction, but using factor to do factor adjustments. And let me see what is factor adjustment. Right? So we want to do high dimensional prediction, just like using macroeconomic time series to predict, let's say, unemployment rates. Right? So all those XT, because are measure economic fundamentals, they are highly correlated. And if you use traditional lasso scale, they will break down because those X will not satisfy conditions that we mathematical statistician or learning theory create, right, under whatever irrepresentable or restrict eigenvalues. Because of their latent factor, none of those conditions will be satisfied. And our method is a very simple principle, right? So it's really lifting. So we call factor adjusted model selection, in which I assume these XT are highly correlated. but driven by a few latent factor plus idiosyncratic components. So I'm going to do a very simple substitution, substitute into here, right? So I just substitute into here, so it would be now expressed in terms of latent factor and idiosyncratic components, right? So in other words, I'll be just substituting in there. And now if I regard this, right, as UT and FT as my covariates, so I'm really doing lifting, right? So in our example, it's 131 dimensional space. So if I extract 5 factors, it's now become 136 dimensions, right? 131 is idiosyncratic components, and 5 is latent factors, right? And the nice part is the beta you want here is the same as beta you want here, right? So now let's consider decorrelation, right? So by definition, these two are uncorrelated, factor and idiosyncratic are uncorrelated, or we could even assume they are independent. And then after latent factor being extracted out, idiosyncratic components here are also uncorrelated. So you are in a very weak correlation situation. So the regularized methods would work, right? So and this is now the only unfortunate thing by doing lifting is this FT and this UT is unknown to you, but we have principal components, right? So you just robustly estimate F and robustly estimated F and UT, right? And now you just using this as predictor, so you are in business, right? So in other words, if you give me this XT, I learn about this FT, UT, and BT, whatever I can learn from the data, right? And now I'm using these as predictor, and it works. So let me give you a very simple, naive example that provides you intuitions, right? So in this case, is high dimensional regression. My beta depending on the first 10 variables, and typical lasso break down easily because there are a few, the non-zero component is too big. Anyway, and then also correlation too big too, and the remaining are 0, right? This epsilon t, I just give you very nice normal, right? And this xt is very simple, just equicorrelation covariance matrix sigma here, right? So in other words, there's one latent factor that drives the dependence among all those xt's. So it's a one factor model, if you like. So if I do naive 250 dimensional regression, and I apply lasso, so the model selection consistent rates of lasso is very low. As long as rho a little bit over 0.2, it'll be 0%, right? So in contrast, if I learn from the data, so I will extract one latent factor. So I'll now run 251 dimensional, right? One latent factor plus 250 idiosyncratic components. My model selection consistent would be 100%, right? So this is one example. If you believe, say, hey, this covariance matrix sigma is too simple, can you give me a little bit more realistic covariance matrix? I do the same experiment, just change this covariance matrix to be the covariance matrix calibrated to SP500 components of the data. And the story, I mean, the detail probably not important. The story is the same. You could get 100% model selection consistency based on our factor adjustments, whereas other methods, including SCAD, have pretty low model selection consistent rates, and in terms of prediction error, so will be also the smallest among all. And this is just saying that this method can apply to logistic regression, not only linear regression, because there's no, when you do factor adjustments, right, it's not really a limit to linear models. So anything with generalized linear model will continue to apply. And this just show you for, let's say, true factor model, you have high selection consistent rates, whereas lasso have very low. And similar for equicorrelation model, and even for uncorrelated case, you don't really pay much the price. Sometimes you could still gain a little bit. So this is just showing you that you can do it. And if you're really curious for our macroeconomic time series, if I apply the model selection methods, I just curious which variables influence more on bond risk premium, right? So first of all, you can use inform select with factor adjustment, without factor adjustment, and principal component regression. So this is out of sample R squared that we will get for each of those. But this is not the important thing I want to emphasize. Just want to show you that you could actually see which variables that actually matter to it. So among those is I think, let's say, non-farm, like a commodity price index, federal fund rates versus BBB like spread and so on. So these, let me not get to this either. I just want to show you, this is just a prediction outcome. Again, I just want to show you it's very simple. We write a software, you could just issue form, select X and Y, and you just say linear regression equal to false, or default is false, is do linear regression. You could also do this for logistic regression just by setting this to be true. It would tell you how many factors you found and what is the estimated coefficients and so on. And the factor adjustment can not only apply to to the selection of models, can also apply to doing the inference. So we ask typically the same question as Barr's paper in Journal of Finance asked, how many mutual fund has positive alpha? So in this case, right, so let's say I observe 1,000 mutual fund over, let's say, 3-year period, right? So and I ask myself, is there have positive alpha here? So and this one is equal to syncretic errors, right? The error, noise. Noise now it decomposes into 2 parts. One part is factor part, the other part is equal syncretic part. Now I have 2 methods. One is naive, right? I just calculate mutual funds average performance and use this as a test statistics. So this test statistics average performance over 3 years would be dependence because there's latent factors due to style rise, herding effect, whatever you could explain it. Right? And secondary, also as importantly, is bigger noise because these 2 components together you think is a noise, right? So now if dependence help us, so if we use principal components to learn about latent factors, though I could subtract those parts, right? So my noise is not only this part. So first, this part is weak dependence and it reduces noise. And you are in much better situation to do this. Right? So I know it's a very late and the lots of material, I tell you, a lot of high-tech things all relate about factor models. So let me just do a simple simulation example. Hopefully that will be enough to convince you it's a very simple methods. Okay, so in this case, I just simulate 3-factor models, right? I think that is 3-factor models. And this is latent factor, this is equal syncretic components. It's just a little bit detail how I simulate this, and how I simulate the noise, right? So these just a bit more detail on that. And then I assume that I have observed data over 100 days or over 100 weeks, right? And the P is 500 stock or 500 mutual funds. Among those, 1/4 of those has positive alpha, and the remaining doesn't have. So if I use naive ones, I just calculate sample average of those 500 mutual funds. I would get 500 sample means. So this is the distribution of 500 sample means. So you're barely able to see there are 2 groups of them. One group has skills, the other group has no skills. So you're barely able to do it. So if I learn about latent factors, right, and then subtract those out, the noise will be smaller, and this is what you see. So you'll see there are 2 groups of people, 1/4 of those have skill, the other have no skill. And because the noise here is T distribution, is heavy tail, so if I apply our robust principle to this, you'll get in this graph, right? Basically separate these 2 groups, right? So, and this one, we give a method called, again, everything called form test, factor adjust robust multiple testing, right? And if you ask me how difficult to implement it, very easy, right? So you just say install the software, and then you just say output of form test X. If you have 1 sample, if you have 2 samples, you form test X, comma Y, it will give you exactly, right? Tell you how many dimensions you have, right? So this is a simulation model I have. What is the sample size that you have? How many factors I learn, right? And then what I control FDR at 0.5%. These are the variables that I select, right? So, I mean, there's 1 fault discovery here for our simulation. I know which one it is, right? And then it also output what's so-called adjusted p-values and so on. So it's very handy to use, if just in case you want to use. So there's a lot of talk so far. I know. So let me just quickly wrap up so that at least I leave you not so bad impression, right? If I talk for another 2 hours, I'm pretty sure you'll never come to my talk again, right? So let me just give you a refresh what we have talked, right? So first, financial data involve heavy tails, and actually heavy tails everywhere for big data, because by chance alone, some variable will have heavy tail, and you know that Gaussian subnormality is a fiction of mathematical statistician or machine learning theories, right? So, and I say, well, how do we remove fiction to reality? Is that you're just doing simple truncation. Truncate at high level, square root n of your standard deviation, then your truncated mean would behave as if you observe like Gaussian data. And in the regression situation, you just truncate the loss so that you could use Hilbert loss, we call adaptive Hilbert loss. Right? And then the second one I basically saying is factor model is everywhere being used to model about the dependence, right? I mean, the cross-sectional dependence or dependence among different gene expressions. And typically, you observe other variable too. In some cases, you think pharma French are proxy factors. In other cases, you think that the Fern attributes, the Fern characteristics, is the information that you could use to help you learn about time-dependent, factor loadings. So in this case, how do we blend those information into the analysis? I basically say you do robust fitting first, right? So in other words, you do projection first, and then now you apply PCA to it. Then this way, you actually, using your site information, learn about common factors. And also we use one example just to show you how can you create prediction indices to predict bond risk premia. And then the third one, right, I talk about is, the factor adjustments, right? So if you really want to do variable selections by using modern statistical machine learning methods, because your variables are highly correlated, it's easy to selecting the wrong guys for interpretation or for whatsoever reason, you could do lifting. And this lifting we call farm select, right? So you could just regress your Y variables on what you learned the factor and what you learned equal-significant components. And then this way, you'll be the classical theory on dependence would work, right? And then the next one is that you learn the factor and subtract those common factor out. Actually, you decrease the noise, so therefore increase the noise to signal to noise ratio, and also you decrease the dependence. In terms of application, there's a lot of applications. Today, I basically tell you how to combine market signals for high-frequency trading, how to forecast bond risk premiums, how to validating whether the factor or SP500 will work, how many percent haven't been explained in the markets, right? And we actually also have work. Unfortunately, I don't have time, and it'll also be too long. We're also using this to predict duration and direction of high-frequency finance. So if you're asking if the ticker move, the next move is up or down. Right? So this is really the direction. How long that duration will be, that will be the duration. And as I said, I see lots of paper doing very exciting applied statistical machine learning methods to do asset pricing. And most of the thing is trying to understand how the factor loading change over time. And this is typical model through its dependence on Fern characteristics, and therefore you can apply statistical machine learning to it. I know it's having a lot of materials, but I would be happy to answer a few of your questions. Thank you.
We have a naive question. So your truncation depends on the estimation of variance. Mm-hmm. So is it possible to get better if you have a robust estimate for the variance?
Right. This is a very good question, right? So in our implementation, we do have to rely on our estimation, and of course then you do like a truncation on the data, right, to estimate the variance too, right? So we do this, right? Another way that you can do in a lot of those in software implementation, we do a lazy cross-validation type of idea just to select those where is the best trade-off between that, right? So one is theory, the other is in application. We do cross-validation or we do robust learning and then estimate it. But robust learning, at one level, you always have to specify, right, the hyperparameter. So yeah, we do cross-validation.
I see.
Yeah, at that level. Yeah.
So in truncation, actually, it's a component-wise truncation.
Right, it's a component-wise.
There is something like Tukey's median history to high-dimensional.
Right.
Robust. Do you think that's possible?
Well, right. So very good question, right? I noticed that you write a very nice paper on GAN and Tukey's median, right? So it's a very nice paper. So I'm pretty sure median, you can do it, but median is estimating median. It's not estimating mean, right? So when I estimation, let's say covariance, right, is expected of x squared. You cannot say expected of median of x squared. Right? So what I'm trying to say, when you estimate in Tukey median, so let me say two ways. Let me interpret the median first, right? So you are really estimating median. You are not estimating mean, right? So when distribution is asymmetric, we are estimating two different, very different quantities, right? And now you may ask why we care about mean. If we only estimation location, I would agree the median would be another measure. But when we are estimating the variance or volatility matrix, right? If I use the median as operation, all mathematical intuition will be disappeared, right? So when we talk about portfolio variance, we have a nice formula. You have to talk about portfolio median-based variance or whatever dispersion will be completely destroyed, right? So median is not an easy substitute of mean because of volatility and other things, right? Right. And then this first, right? The second, I know you are a friend, so very implicitly criticize that I only doing truncated components-wise, right? So you could easily do, let's say, use statistics, right? I mean, like use study for estimating the covariance matrix, and now I can truncate on the norm of my statistic too. So I didn't talk about it because it's not on covariance matrix estimation, but you could do also the whole vector, right? So if you give me whole vector, I could create, let's say, normalized statistics, and then I just truncate on the norm of that variable. So you could do this too. So in other words, sample covariance matrix can be written as a U statistics.
Like
U statistics, I could divide by norm and multiply by norm, and now I truncate on the first part of the norm. Right? So you can do multivariate version too. Yeah.
I see. Yeah, well, actually, recently we can do robust scatter matrix estimation using the GAN approach.
Right.
Yeah.
That's a very nice paper. Yeah.
Okay.
Yeah.
Thank you.
Nice. Yeah.
So in your multi-index model, the middle step was bringing the edge function seems to be the most mysterious part. So can you tell us a bit more about how you choose the network, how you choose the layer network?
Okay, yeah. So this is a very good question. So there are two parts, right? So one part is that how we choose it, and second part is how you could choose it, right? So there are many versions, right? So like something like this, right? So right. So after I extracting the latent factors here, right, and then we creating the indices and to predict those y's. So in this case, we are doing very lazy version. We just doing additive model. So we do additive model. So it's really what we are doing here. It would be called projection pursuits. So I find a few indices from slide inverse regression, and then just doing this additive model. So we choose one or two index according to data-driven version. Of course, you can also from here to here, you can apply a small learning like algorithms, right? So let's say deep learning algorithms. Right? So the essential difference is that the deep learning algorithms usually activation function is given by you. So therefore you use, let's say, ReLU function or sigmoid functions. In our case here is a non-parametric function, so it's a data-driven learning activating functions. Does that answer your question, how we do it? Yeah.
Yes, thank you.
So in the slides about factor adjustment, and there is a histogram comparison between the sample mean and the factor adjusted mean.
Okay.
So in the the previous one.
Okay. Yeah. Okay. Sorry. Yeah.
I think if the latent factor is also mean zero, so how come the estimated?
Oh, very good
sample is
question.
different?
Yeah, very good question. And what make it difference, right? Yeah. So this is very good question. Right? So the when I do average, or call this sample average of this guy, would be close to zero, technically speaking. We close to zero, but not exact zero, right? So when you divide by, technically XF bar here would be of square root n order. And this is square root n order actually is the variant that you're showing here. So when I do, so in other words, when this has mean zero, but the F bar itself will not be exactly zero. So so this is I think where is the difference lies. So it's like when you don't do factor adjustment, when you do the sample mean here, you still have this number there of square root n, and this is the order that actually the order actually carry here. That's why you don't get it very big, but it's in between big enough to merge these two modes.
So maybe the effect about robust estimation.
But the effect of robust estimation making these two separation more, just like you reduce noise further. Yeah. So sample average have a kind of robust. It's just 100% robust. If I have a kind of robust operation there, yeah.
Other questions? We can also continue the discussion afterwards. So thank you again, Professor Fan, for the wonderful lecture.
Okay, thank you, Ying.